All right, welcome again to the second day, and sorry for yesterday's interruption, but I figured out how to do it, not why it happened, but how to do it. Okay, so yesterday this is where we had stopped. We were talking about two events, A and B, and our stopping point was that this is taken as definition of probability of A given B. The probability of joint event divided by probability of the conditioning event. Whatever we have observed is called conditioning event, and one can justify it by applying it to simple scenarios and justify ourselves that yeah, this is exactly what we want, and then we take it to more general scenario. Okay, so that's where we were yesterday. Now let's come to this was about conditional probability. Now we can come to what is called conditional expectation. Suppose you have a random variable x, and it's integrable, so summation of those probabilities is finite, summation of weighted averages is finite. Now recall this was our definition of expectation, summation over x times probability capital X equal to x. So this is the weighted average, weight is x and these are the probabilities. Now if you take the weighted average of the conditional probabilities, that makes sense to call it conditional expectation. So if you have observed an event, then this will be your new expected value of whatever is your reward. Okay, and this is simply an expectation with conditional probabilities instead of probabilities. There is no deviation. It has all the properties like absolute values and so on. What we have taken, it will work. Now, suppose you have two random variables, and what we are observing is an event based on a random variable. So it's not just whether B happened, yes or no, but what is the value of y which happened. Okay, suppose we observed a random variable y, then the same definition that we gave above, here it was given a b, event b. Instead of that, the event b is now capital Y equal to small y, and the same definition we can give. And then since this conditional expectation is similar, exactly expectation with respect to these conditional probabilities, the Jensen's inequality will also hold. We will not spend time on that, but this is easy enough calculation. As I said, finite dimensional is algebra, otherwise analysis, simple. Now, here is the important screen. That is, we defined this definition, conditional expectation of x given capital Y equal to y. And whatever summation we get, it's actually a random variable. We can think about it as conditional expectation of x given y is random variable z, which depends on y, and when y is observed as little y, then here is the value. So we can think about it as a let's say in the stock market, the boss gives an instruction to his people who are going to be on the floor. In the old days, now they are doing it online, that if, let's say, Y is Infosys, X is TCS. So if Y, the Infosys stock moves to such and such value, here is the expected value of X, and now you do what you want to do. So in order to implement that, you have to make a table as to for every value of Y, we can write down what will be the expected value of X. So in other words, you will get a function of Y. Okay, so that is what it is. This g of little y is conditional expectation of x given that capital Y is small y. You compile it as a function, and then we say that conditional expectation of random variable x given random variable y is z, where z is a function of y, and that function can be computed by this nice formula. Okay, so any kind of policies, definitions that you want to give, we can give in terms of conditioning, because when it comes to conditional expectation, because when it gets time to implement something, you would have observed some things, and you can plug in those values of what you have observed in a function to compute what should be your expected value. Okay, so important, conditional expectation of a random variable x given another random variable y is itself a random variable, and that random variable is function of the observed random variable y, and that function is defined by this formula. Okay. And all that we talked, y need not have been a real value. Whatever we talked will also work if y was taking values in a d-dimensional vector space, or if y is a vector, y is you have random variables x and y1, y2, ym, then expectation value of x given y1, y2, ym is a function of the observed variables. And what function? That function is now worked out here. Okay, so it's simple enough thing, and now I'm just showing them. I'm not going to even read them to avoid time, but basically linear, all the properties that we work with expectations work with conditional expectations. So linearity works, monotonicity works. Here is an interesting observation that if you are interested in conditional expectation of y given u given y1, y2, yk, we can first take condition with respect to y1, y2, yk plus 1, and then take another expectation given y1, y2, yk. And best way to think about it is, if you have a point in a three-dimensional space and you want its projection onto x-axis, first we can take its projection on the x and y axis together, the plane containing x and y axis together, and then take from there, you take a further projection onto the x axis. The same, you will get the same answer. So in a certain sense, this is the same business that you first take a conditional expectation with respect to, assume if you had a few more variables available, it will be a function of whatever you are conditioning with. It will include what y1, y2, yk. Now you take conditional expectation with respect to y1, y2, yk. And especially in finite spaces, all these are simple algebra. We can verify these values via algebra. Okay. And why I've only given one more, you can given many more also, the same thing works. Expectation of y, u given y1, y2, yk plus 1 up to ym, and then y1 to yk is same as expectation u given y1 to yk. So instead of r2, r3, we can do r, rk and rk plus m. Same thing will work. So I've glossed over a few slides. These are some algebraic properties of these conditional expectations. You can go over when you see the have the presentation along with the videos later. But let me focus on this interesting thing now. Let's consider a gambling house where n games are going to be played sequentially. So earlier thing, there were two coins, two dice were being tossed at the same time. Now there is a game which will be played sequentially. Same game, different game, doesn't matter. Let xk be the net reward for a stake of ₹1 for the kth game. If somebody bids ₹1 on the kth game, they will reward his xk. And let's say it's a fair game. Expectation xk is 0. Rare to find, but suppose it is so. Now question is it possible for a gambler to tweak the system by choosing A1, A2, AN such that by betting an amount AK on the kth game, the gambler can turn the game in her favor? Okay. So this question was occupying the probabilists who are associated with gambling and probability modeling in the 16th, 17th centuries. Okay, that so there's something called the Petersburg game where sequentially it is going to be played, and you bet ₹1 and you may win or you may lose, half of probability. If you lose, next time you pay bid again, and now you bet ₹2. And each time if you win, you will get twice that, and if you add it up, eventually you would have won ₹1. And if you continue to lose, each time you double your stake and keep playing. And then there is a debate whether effectively this is a sure strategy of sure win, or is there something else. Okay, and more about this question in a few minutes later. But so the point is, if the time amounts you have to bet are deterministic numbers, constants, then we can see that the expected value of Sn will be summation ak expected value of xk, which will be 0. So on the average, anyway, you are going to lose. Now the question is, if AKs are allowed to depend on the history. So while betting at the kth time, because it is sequential, you would have observed A1, A2, AK minus 1, XK, X1, X2, XK minus 1. You utilize this information to bid kth game. Like in my betting thing which I told you, if you have already won, you can stop playing, you are not going to play. And if you keep losing, if each of X1, X2, XK minus 1 is zeros, then the kth game you bet 2 power k. Your AK will be 2 power k if x1, x2 up to xk minus 1 is 0, and 2 power k if yeah. So then you will get eventually that you will win 1. But there is a catch to this. With a small, let's say you walk in with some money in your pocket, total money you have. If you lose first k games where 2 power k is bigger than the money you have got, you can't now bet 2 power k, and you will be thrown out by the gambling house. So therefore there was debate whether this gives you a sure way of winning or not, etc. How does one interpret it? Okay. Now, to be what kind of things can go wrong? Let's see. Even in finite time. So this was a thing going to infinite time. So suppose you are not going to keep playing. You suppose only 2 games or 10 games. Then what happens? So let's say fair coin is going to be tossed twice. A gambler has a choice of betting in 2 games. Bet 1,000 on first game gives 1600 if the first toss is edge, and yield 0 if the first toss is a loss. Okay. And on the game 2, the bet of 1000 on the second game gives 1800, 350 or 1450 depending on these 4 outcomes. And now I have drawn it as a graph. Okay. So this is the first one, and these are the outcomes of the second toss. Okay. So 1800, 150, 1450. Now the expected return for the first game is 850. This times half plus this times half. And we can compute expected return for the second game, and we'll see it is 900. So it is both are less than 1000, and therefore our law of large numbers will give that if large number of people play this game, the gambling house is going to make money. Now, novelty of the game designed by an expert was lost after some time, and casino owner tried to entice more people by making it more interesting. So the game show host asked people to bet without deciding if it is for game 1 or game 2. Namely, you start playing. After game 1, if you don't feel like, you can exit. If you feel like, you can continue to game 2. Okay. Now, let's do, if it's a smart gambler, he or she will do the following. Suppose first round you win, he or she wins. They are here. Now they have to choose not originally what they had bet 1000, that has already gone up to 1600. Now they have to decide whether or to not continue to play the game. 1600, if you again get a H, you will get to 1800. But if next one is a T, it will come down to 100. So the expected return after the second game here is 950. So you have 1600 in hand, whereas expected return after second game will be 950. So why would you play? Whereas on the other hand here, 100 can go down to 50, but it can go up to 1450 with probability half. So it will go up to 750. So you have lost it, but you have chance of making it up somewhat. You initially started with 1000, it is down to 100, but you can get something at least if you play one more round. And so a smart investor will quit if he or she reaches 100 and will continue to play if he or she reaches T, and then the final rewards will be these three green things. So 1600 with probability half, 50 with probability half, 1450 with probability half, and you get that the net reward becomes 1175. So what was fair game which was in favor of the gambling house, as soon as players were allowed to decide to stop or play after first round, the game changed its hand and it became favorable to the player. So whenever one of the two sides has an option how long to play, okay, the overall analysis changes. And a brief foray, these days, for years now, if somebody wants to buy a house and goes to bank for a house loan, several banks give a choice. You can choose for a fixed rate of interest or variable rate of interest. So fixed rate of interest you have for some number of years, then it has one rate, and if you say variable, then it has another rate. And most banks have this law that if you have made enough money otherwise and you want to pay off all your loan much earlier than the promised period, then there is a kind of a penalty. And various people did not understand that, if I have taken a loan, suppose I take a loan at 10 interest rate of 10%, and after 3 years, I have taken the loan for 10 years. After 3 years, I somehow see that the interest rate has dropped in the market. So I can borrow a 8% loan from some other bank and return this bank's loan right away, so that I have reduced my payoff to the bank. In other words, by switching from one bank to the other, I am able to simulate or to redo the game 1, game 2 scenario, where I am able to choose how long to take this loan for, depending on how the interest rates are growing in the market. On the other hand, if the market interest rate goes up, then I need not do this. So if the borrower is allowed to pay back the loan ahead of time of the initial plan, the bank charges an extra interest. And there is a lot of literature on this. Even some people have gone to the court, and court has overruled that how can you charge a penalty for paying back your loan. The courts did not understand the strategic part of this. So now what banks do is they put whatever penalty they would have imposed, they already put it into their interest rate. They have raised the interest rates because they are forced to give the person a choice of paying back early. Okay. So maybe I said it a bit too fast and didn't explain it completely, but you can read about it, talk to each other, or write to me if you have still question mark about this. I said brought this example because it's not only about gambling, it is day-to-day life. We're dealing with banks, dealing with courts, all this what I call strategic decision making, or sequential decision making. You need not commit it now. You can change your plan as the time goes by. As the time goes by, you hear and learn more things, and you can fine-tune your strategy based on that. The other side has to be prepared for that. Just like after giving you a 6-year loan, after 1 year, bank can't say that sorry, you have to pay back all the money right away. That is not allowed. So bank is forced to give you for a fixed period. Then it is reasonable that bank asks you to hold the same period, and if you repay early, then they may charge a premium for that. Okay. All right. Now coming back to the gambling, if the gambling house would like to see that the game remains favorable to the house in spite of giving the choice to players, it could ensure that at each node, the reward at the end, reward at hand is greater than or equal to the expected reward after one more step. So the left hand side here is the expected reward, but if the player plays one more step, and the right hand side is reward at hand. You have reached the point, sequence of events has been S1, S2, Sk, the sums. At time k, this is the reward at hand. If you play one more, reward at hand is Sk plus 1, then they should ensure this. Of course, they have to ensure that overall expected is less than whatever they have charged you to play. But once they do that, they can be assured that any kind of strategic game, you are not going to tweak the house against house. So here is a pictorial. If you recall, the first two things are the same. The bottom line, what I've rearranged the winnings, and now it is done so that here it is 1600 in hand, and this is 1575 if one more turn, 100 in hand, 75 if one more game. So this ensures that no matter how the strategy a gambler plays, as long as you have enticed the person in gambling, you are ahead. You meaning the gambling house. Okay. So if such a thing can be ensured, then the sum of the total net reward at each point, that becomes what is called a martingale. So here is a martingale. This is S0. S1 is 1600 or 100 with probability half-half, and HH will correspond to 7. So this is S2, the total sum, S1, S2. And here this picture is less than equal to is one thing, but if it remains equal, then it is called a martingale. The sequence of rewards is said to be a martingale if at each step the reward at hand, if the player exits at that step, equals the expected reward after one more step. Or writing this, we can write as conditional expectation of Sn plus 1 given S1 is A1 up to Sn is An is An. So A1, A2, An are the nodes, and it is equal to the last node. Okay. And less than equal to it is called super martingale, sub martingale. Less than equal to this happens, it is called super martingale, and greater than equal to it happens, it is called a sub martingale. So there are this sub and super, which are each for every n, for everywhere it is greater than, same inequality holds. If this is greater than equal to n for every n, it is sub martingale. Less than equal to this, it is super martingale. Now, here is the interesting thing. Now, suppose we start with a martingale. So net reward at time n for an initial bid of 1, and it's a martingale means at each step, one step, nobody can tweak the game in their favor. You play one more step, the expected return is same as whatever you already had gained at that point. Now, let us consider a predictable strategy. So I have called it the word predictable, which is like at time k, it's a function of random variables, but random variables observed up to but previous round, not this round. Because this strategy you are implementing now before the kth game is played, so you can have a strategy which uses all the earlier ones, but not that one. And then if you bid this quantity, the reward will be fk at s1, s2, sk minus 1 times the. So you could have exited with sk minus 1, you chose to continue, so your additional will be sk minus 1. So the net reward for this strategy, so f1, f2, sk all together, we can call it as a strategy, and this strategy at time n, the reward is Zn.
Someone has a question actually.
Let's see if I can see what the question
is. Is Sn a random process?
Yeah, what is the question? I can't see.
Is Sn a random process?
Yeah. So this SSR random process, and these are. Let me go back to my. Yeah. So this is S0. Okay. S1 is 100 with, if the first outcome is T, it is 100, and is 1600 if the first outcome is H. This is S2. If the outcome is HH, then it is S2 is 1700, HT it is 1450, H is 50, this should have been TH. TH it is 50 and TT is 100. So you have some sequence of games which are happening, and SK is the net gain at time K. If you start with one at time 1 with my indexing, this is S1, S2, this is S3. Sorry. So
Why is it called martingale?
Why
Why
is
is it called martingale? What
Okay.
is the motivation for the name?
The word martingale itself is somehow related to horse racing. Okay. And therefore, whoever there's a mathematician, probably is called Ville, who called it martingale, and that name has stuck. Okay. Other than that, I can't figure out why this name has come, but it seemed an interesting enough name, and that's why it has stuck.
Oh, I thought maybe name of a mathematician. I mean, probably.
A mathematician. It's something to do with horse racing.
Okay.
So
Thanks.
So once again, so another way to think about it is a sequence of rewards S1, S2, Sn. So you have made some initial bid. If you stop after one round, you will get S1. If you stop after nth round, you will get Sn. If these rewards are stacked in such a way that at any time, if you decide to play one more round, your expected reward is same as expected reward will change, but expected is same as whatever you have in hand. That is what this is. Expected reward after one more step is same as whatever you have in hand. And so if to begin with, if the only thing which has been allowed is you decide how many games you will play, that means you are committing to a strategy which is you are exiting at a fixed time. And this S1, S2, Sn are already created. Now, if they are arranged in such a way that conditional expectation of Sn plus 1 given S1, S2, Sn is Sn, then the gambling house can give you a strategic game that anytime you choose, you want to continue or stop. If you want to stop, I will pay out whatever is due to you, or you play one more round and you will get whatever is next. So if your strategic play is allowed, then your net reward can be listed as this Zn that we have listed here. Corresponding to a strategic game F1, F2, Fk, strategy F1, F2, Fk, dot, 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 the rewarded time n will be Zn. And then this is a major result from Doob that if to begin with S is a martingale, the reward sequence is a martingale, then any kind of strategic play involving predictable strategies, the expected return will continue to be the same. Here is the theorem. Let F1 be a constant and Fk be bounded functions. Sk is a martingale. Then Zk defined by this is also a martingale.
There is another question right now.
By a strategic play, if to begin with the game is a martingale, you can't tweak the on the expected value of the game by this. Major result from Doob. So essentially, the martingales were not defined by Doob; they were defined by, I guess, Ville and maybe Paul Levy, and they had wrote about it. But Doob took it into account and worked out a whole lot of major results about martingales. All the three results we are going to do today are due to Doob, and they are the cornerstone of using martingale theory for anything and everything in probability theory. Okay. So this is the first such result, that if to begin with Sk is a martingale, namely the expected condition that we wrote down, you tweak the things via strategic multipliers, strategy FK, which is predictable because at a, so if you look at this object, FK, this, you will have to implement this at time K. It's a random variable, but it's a random variable which is already a constant when you reach that time. So therefore, this is a very interesting kind of a random variable, because here you are fixing some sequence of observables with time, and all discussion is based on that sequence of observables, and therefore we can talk about it at time 0, or at time 1. It may look like a random variable. When the time k comes, you will know what that value is. And if you think about it, in our real life also, we are used to talk about future times which are not deterministic, but which when the time occurs, everybody will agree that yes, time has happened. It's like, for a Zoom session, we can say that as soon as number of participants crosses 50, we will start the session, or 2 minutes after that we will start the session. To begin with, we don't know when that time will be, so it's a random variable. When are you going to start the session? But when 50 people come, even if whoever is going to speak is not realized it, somebody can remind me that, oh, now the participants are 50, now we can start in 2 minutes. Should have put it off, but yeah. So this
Raju, there is a question.
tell me.
If from Durga, if expected award will remain the same, why will anyone be interested to play?
Okay, so this is an idealized game. No gambling house is going to offer this game. Okay, in fact, every game, always the expected reward is less than what you are supposed to play. Okay, so the reward, one can question why do people play, because they somehow think that they can play a strategy which will surely lead them to victory. Also, you think about the following. Let's say the so-called lottery tickets. When I was a child at school, the lottery tickets used to be 1 rupee. I don't know what are the lottery tickets today, but let's say which are legally done in India, 100, 1,000, I don't know. But if you read out how many they are going to sell and what will be the profit, what will be the reward, etc., you can figure out that the expected reward is a minuscule fraction of whatever is the pay that everybody buys the lottery ticket. But still, so many sell. The reason is that people are willing to lose 100 rupees today if there is even a minuscule of chance that they can win 1 million. That people will play. So why people play is a very difficult thing to answer. Okay, but so these are idealized. We are doing an idealized analysis, and while using it, you have to use your own judgment of what the framework is. Okay. I hope I answered the question. Now, briefly, I'll go over the proof. Just 2, 3 lines here. That let's note that the difference in Zn and the difference in Zn will be exactly equal to what you will get at the nth time, Fn S1 S2 Sn minus 1 times Sn minus Sn minus 1. Now, when you try to do conditional expectation of this, we will see that this will I have changed the index n to n plus 1 here anyway, but doesn't matter. If you try to do conditional expectation after at time n, if you have observed up to time n, conditional expected reward at the next time is equal to what you have at time now plus this expectation, which this being a constant at Sn plus 1, a function of Sn S1 S2 Sn minus 1 Sn. So expected value when you take of the product, this can be pulled out, and correct. This should have been Sn plus 1 here. Fn plus 1. Okay. So then when you take conditional expectation Zn plus 1 given S1, S2, Sn, Zn which is already there will be come out, and conditional expectation of this given the observables, this part will be observed at time n plus 1 already, so it will be taken out of the expectation and it will be this. So here we are using something that expected value of some h of y times x given y will be h of y times expected value of x given y. So think about it this way, that if you are at a time when y is already observed, then the function h of y is already, you know what its value is. So you don't, while taking expected values, you don't need to take it out, you will take it out and then times expected value x given y. So if expected value of x given y is 0, expected value of hy times x will also be 0. So therefore, conditional expectation of Sn plus 1 minus Sn is 0. So when you multiply it by this, it will still be 0, and you will get this is equal to 0. So if you try to write out these steps involving summations and functions of the observables, you can easily write it out. So so this transformation, so you had martingale Zns, and this you have transformed by multiplying by some constants, and in such a way that these constants are predictable and you get Zn. So this is called a martingale transform of the martingale Sk. Sk is our original martingale, and then we have multiplied by some strategies and multiplied the increments via strategies and taken the sum. Now, as we can see, if you go to a continuous time, this is like the sums. This is like the Riemann sums, and in the limit, this will be like an integral. So the analog of this object in continuous time is what is called the stochastic integral, and again a major part of applying probability to markets or to various other things. Okay. And what I wrote in discrete time, the Doomb's theorem continues to work in continuous time, that if original Sk is a martingale, then when you take its stochastic integral with respect to a predictable integrand, the output is still a martingale. But today we are not focusing on that. The focus here is that if S is a martingale, then Z defined by this formula, S is a martingale sequence, then Z defined by this formula is also a martingale sequence. That is the main theorem. Okay. In mathematical finance, when Sk denotes the price of a stock, then Fk, S1, S2, Sk minus 1 is called a trading strategy. So on kth day, whether you want to buy, sell, how many to buy, how many to sell, of course you can bring in all the happenings of till yesterday and decide. Based on that, you can decide how much to buy or how much to sell. Or you may be controlling the thing, you can tell your people how much to buy or how much to sell. So this is called a trading strategy, and this yields the value of the net holdings by this strategy. Now, it's clear here that for a trading strategy, one could bring into all the other observables and not the only history of Sk. So in other words, if somebody is interested in, let's say, bidding for Tata TCS, okay, and Sk is denoting the TCS shares. Now, how much to buy TCS shares, you can depend based on whatever happened in TCS shares till yesterday, but you can also see what happened in Infosys shares, what happened in other stock shares, or overall what happened in the economy or anything else. So you can bring in all the information available till yesterday evening in this decision. Okay. So in other words, the strategies need not be only depend on what happened on S1, S2, Sk, but whatever other variables you think you are going to be able to observe. So that leads to this general framework that you can denote all observables at time k by yk. So it need not be one real valued function or one, but it could be a multidimensional function or whatever you might want. It could be a very generic function of observables. And then you can choose Sk, whether to include or, and this should include Sk, but could include more. And now the trading strategy on kth day could be Fk of y1, y2, yk minus 1. And the thing would be, as long as the stock market is a martingale with respect to these observables, so here is our final definition of martingales, let yk be a stream of observable random variables. For each t, y1, y2, йт's are observed, and the sequence of random variables yk is said to be a martingale with respect to observables yk if mk is observable at time k, that is mk is a function of m1, m2, m. Here I should have put, again I made a mistake. Mk is a function of y1, y2, yk, and conditional expectation of mk plus 1 given y1, y2, yk is mk. So now in stochastic process literature, instead of saying observables with respect to a sequence of observables, it will say given a sigma field. And that is something which always bothers others who want to use stochastics in their understanding. They wonder what do you mean by given a sigma field? So one has to always read it as given a sequence of observables, and that sigma field is sigma field generated by these observables. So any of you who try to read anything in stochastic process literature, if you just make this transformation, that a filtration or a sequence of sigma fields is just a collection of observables. Increasing sigma field means observables are of course increasing. Whatever you observed yesterday, you can't undo. You can only observe more if at all. So sequence of observables is increasing, and measurable with respect to sigma field is, you can think about it as a function of the observables at that time. All right. So martingale is something which is observable at time k, and expectation of mk plus 1 given observables up to time k is equal to mk. This is said to be a sub-martingale if the equality is replaced by greater than equal to, and sub-martingale if it is replaced by less than equal to for every k. So this is what is a martingale, and so now in what follows we are going to fix a stream of observable random variables, and the class of martingales that we talk about is martingales with respect to this sequence of observables. And now you can figure out that the class of martingales becomes a linear space. If you add two martingales, you are going to get a martingale. This may not be true if you are restricting notion as we were discussing earlier. So this property that class of martingales is a linear space will only come when we are fixing a stream of observable random variables, and our definition of martingales is with respect to this observable stream. Okay? Because here M is a martingale means this, and let's say W is a martingale will mean Wk is observable at time k, it's a function of y1 to yk, and conditional expectation of Wk plus 1 given this is equal to Wk. So if you take Mk plus 1 plus Wk plus 1 and Mk plus 1, sum of them, conditional expectation will be sum of the conditional expectations, which you will get Wk plus Mk. So trivial to work out that the class of martingales becomes a linear space. And now this is the martingale transform. When we are dealing with martingales with respect to some observables, the strategies are also predictable with respect to those observables, and then very easy to verify that it leads you to martingale transform. The transformed object is still a martingale. If M were if M was a submartingale and Fk is non-negative, then the corresponding object remains a supermartingale, stays supermartingale, and submartingale stays a submartingale if the multipliers are non-negative. So martingale transforms a martingale to martingale, but the same transforms a submartingale to a submartingale if it is non-negative valued, and transforms supermartingale to supermartingale if it is again non-negative valued. Okay, so this is our final definition of a martingale and martingale transform. And now I come to another interesting notion. Along with martingales, the notion of a stop time, or some authors also call it stopping times. I myself, in writing papers, sometimes have called it stop time and sometimes called it stopping time. It plays an important role in probability theory and its applications. A stop time tau is itself a random variable. It's a function from omega to the time index set, such that for each k, there is a function theta k, such that the event y tau equal to k is a function of the first k observables. The example that I talked about earlier, we will start as soon as the participant number goes above 50 or greater than equal to 50. As soon as it touches 50, we know. So the event that we have to start would depend on y1, y. If you have to start at time k, it will depend, yes or no will depend on y1, y2, yk. Or we will stop as soon as the number falls below 20. So that's now a stop time, and that again would depend on if yk is the number of people at time k, then as soon as yk is less than 20, we will stop. So it's common life, it is important. We are used to talking about future times which are random, but we will know when it happens, we will know, and everybody will agree that yes, it has happened. So here are examples. Total stop first time total exceeds 10, greater than equal to 10. First case is that sum is greater than equal to k. First time that you hit 0. And we can always say that if you don't want, you can have an infinite sum, or you can say stop as soon as this happens, or you hit the time 10,000. As soon as you hit 0, or you hit the time 100. Right now, because we wanted to avoid infinities, if you can allow infinities in your framework, we need not bring this minimum in mind, and then we can follow our usual convention that infimum over empty set is infinity. So we can define tau to be infimum k mod yk equal to 0. If no such k occurs, then your tau is equal to infinity. So it depends on whether or not we are allowing infinity in our framework. But so this morning we have defined these two notions. So we have a sequence of observables, and then a sequence of martingale, submartingale, supermartingale with respect to that observables, and now a stop time with respect to the same sequence of observables. When time k occurs, if you have not stopped up to then, you have come up to time k, then you know whether you should stop or continue. So while stock market, you can say that you are aiming for some profit. As soon as the stock price crosses something, then you will sell. Next day you sell before the market opens. Okay. So this is actually a special case of the Doo's martingale transform theorem that we talked about, that let tau be a stop time with respect to those observables, and let nk be equal to mk minimum tau. That means you keep moving as long not stop. Once you stop, anyway nothing changes after that. So your net reward remains whatever. So whatever it was at time tau. So nk is equal to m of k minimum tau. If tau equal to 5, then the sequence n1, n2 will become m1, m2, m3, m4, m5, and then m5, 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 m5 dot dot dot. That is our new sequence, which is now we are calling nk. So this is a stopped sequence. So you have a nk was there to begin with. Now we have stopped it at time tau, and then nk is itself a martingale. And we have already talked about that decision to stop or not depends on up to whatever you have observed. So the same thing can be done. We can now write down a sequence fk with a certain thing I've written down, but you can look at it later that it works. And m tau minimum k is actually just the martingale transform of m. You can construct this variables fk so that if you have not got a signal to stop, you will put it as 1, and if you have a signal to stop, you put that as 0, and you will get the stop martingale. So for a sequence, if tau were 3, that will mean that at time 1 you have to continue. So these are 0, and at time 3 you have to stop. So that one is 1, and the same proof shows that if m was a submartingale, then after stopping you are going to get a submartingale, because our multipliers are here 1 or 0, so they are non-negative. So stopping theorem is, to begin with, if you have a martingale, this applying stopping theorem, you are going to get martingales. If it is submartingale, you will get a submartingale. If it was supermartingale, you will get a supermartingale. There may be some typos here, but before I share it with Archana after the sessions, I will correct the typos. I have written some of these slides only last night, so didn't have a way to verify them. So there are some typos. I will correct them. Actually, here is the beauty, that since our framework is only a countable probability space, each of the steps I have written as proof. These are actually we can write down them as a very simple observations and very simple proof, simplest algebra possible, simplest linear algebra possible. Okay. We are not using anything big, and therefore at one go we are able to do martingale transform, stopping time, the stop martingale result, and so on. Okay, and what this means is that if you have a submartingale, then its expected values will keep going down. Here is a major result, again due to Doob. It's called Doob's inequality or Doob's maximal inequality. And suppose mk is a submartingale and lambda is positive, then probability that maximum of mk is bigger than lambda, maximum taken over k less than equal to n, is less than equal to 1 by lambda expected mn. Very interesting here that the right hand side is as in the Chebyshev inequality for probability that mn is bigger than lambda. Okay. But the same estimate tells you that it is also a upper bound for probability that maximum of nk up to k to n is bigger than lambda. That probability stays bounded by 1 by lambda times expected Mn, and other than n occurs only in as an index of m. You are taking maximum over n terms, but the upper bound doesn't involve how many you are taking maximum of. That's the remarkable part of this theorem. And the proof is extremely simple. Suppose let tau be the stop time, which is equal to infimum of k such that mk bigger than lambda, minimum n. So you keep observing mk. If you exceed lambda, you stop there. Otherwise, you stop at n in any case. All right. Then probability that the maximum is bigger than lambda is same as m at tau is bigger than lambda. Because if maximum exceeds lambda, if maximum has exceeded lambda at k equal to 5, our tau will be 5, and m of tau will be 5, and m of 5 will be bigger than lambda. So this probability is same as probability m tau bigger than lambda. And now we apply Chebyshev inequality to the, or Markov inequality to this. We will get 1 by lambda expected m tau. And we already observed that expected m tau is less than or equal to expected mn. So that becomes 1 by lambda expected mn, and that's it. So this is a very major result, and simple calculations that we have done, the proof reduces to just few lines. So what have been the main ingredients in this result? That after stopping also the things don't change. Martingale, martingale, submartingale, submartingale. And what is the main part for that? That was this martingale transform result. Okay. So these three parts, the martingale, stop times, martingale transform, and now maximal inequality. Okay, this is a remark that with a little more work, we can show the following. Let mk be a martingale or a positive submartingale. Probability that it is bigger than lambda is, this expectation is less than or equal to 1 by lambda expected value described like this. And in turn, it tells us what is called the LP inequality for martingales in terms of loop, that the LP norm of maximum is always less than or equal to the LP norm of the endpoint. I just made it as a remark. One can argue this proof, but then we have to write a longer proof. I preferred this version because this version gets used a lot more by itself, and in any case, this is just 3-line proof. A little more work and we'll get the next one as well.